Okay, there we go. Okay, so yeah, so Taskmaster, although it's a lighthearted British comedy, there are themes in there that I think are oddly applicable to doing physics. So in the last few minutes there, you saw the task was for the comedians to blow something substantial off a table. And you saw that the two people there, I think there was Bob and Noel were their names. They said, well, let's test the limits of what a human can blow. You know, it's a very scientific way of approaching a problem. You know, they took some items around them, they put them on the table, and they just tried to blow on them, you know, quickly, just to kind of get a sense, a scale, if you will, of the type of thing that they can blow. So it's a very scientific way of approaching something. And it's amazing. It always amazes me that the average public actually knows a lot about science and the scientific method. They just don't know that they know it, right? It hasn't been a formally taught thing to them. However, you know, once we start talking about these themes in a science class and we sort of draw these parallels, you know, hopefully some of you are kind of having some light bulb moments and saying, yeah, you know, I never really realized that was the scientific method, or I never really realized what I was doing was actually physics. The other reason why I chose this clip was when they were throwing the medicine balls into the bathtub earlier on, and I'll replay that clip a little bit later for you guys, so that way it's part of the recording. That was projectile motion, which we will get to today as well. And projectile motion is, well, put it simply, is to just throw something, and it's subject to the Earth's gravity. So, you know, we do that quite a bit, whether it be throwing medicine balls into a bathtub, or, you know, tossing something to a friend, or playing a baseball game, or, you know, any other sports game. So your brain has an inherent notion of physics, whether you think it does or not. Okay, so before we get too far, I just want to introduce Brandon. So yesterday we had Oksana join us to man the chat. Today we have another TA, Brandon Shu. Brandon, do you want to unmute yourself and just say hello?
Yeah, hi everyone.
There we go. And I think Brandon messaged the chat. He said, hi, everybody there. So, you know, just like yesterday, I think it worked reasonably well. If you guys have questions throughout the lecture, you can just type them into the chat there, and Brandon can hopefully get to them. And I'll check in with Brandon every now and then to see if there's anything that, you know, administrative that he doesn't know, and then I can address. Okay, just some administrative tasks before we jump into the lecture. I want to just review with you. Let's see here. I want to review with you the administrative things for the course, because I've been receiving a lot of emails about this. So if you go onto our course page and you just go to the course schedule, you can see, I'm just going to make this a little bit smaller. You can see here that we are in the first week of lectures. So today is May 5th. And you can see in the schedule here that there are no scheduled labs or tutorials this week. But please don't mistake this for just thinking you have the week off. This was done on purpose, so we don't kind of hit you hard right at the beginning. We want to ease you into it a little bit. So yesterday, after measurement and estimation, students should have gone and opened whatever textbook they're using, whether it be the Giancoli 7th edition or a different edition, or whatever book you found. Every book is going to have a measurement and estimation section in it. And students should have been reviewing the text in that chapter, the themes in that chapter, and doing a few practice problems at the back of the chapter. Giancoli has some good practice questions as well. So you got to make sure you do this kind of on your own. I won't have the time to keep reminding students that they should be doing homework. That should be something that students kind of know to do on their own by now. Coming up in the near future, you have your first assignment due on May 15th. As I mentioned, there are two parts to that assignment. There's going to be the handwritten assignment, which I believe is already posted. And then there's going to be an online component. Now, the online component isn't quite ready yet. We have other technical problems with getting these quiz banks kind of developed, because we're moving things online out of nowhere all of a sudden. So things are kind of a little bit behind, but I'll make sure I get that up and running for you guys as fast as possible, and I'll notify you when that's there. And then 2 days later on May 17th, you have the introductory assignment. I've got a few emails about that from students, so that's good that you, at least some of you have started on that. So if you haven't, I would encourage you to at least look at it sooner rather than later. I love the emails. To me, I mean, they're a great way to communicate with me and get questions answered. However, I will remind students that we're trying to use the Piazza message board, and then that way I'm not having to answer the same email 20 times or more. It's there for everyone to read. And actually, with the Piazza discussion board, other students might actually get to the question before I do. And that happened actually, I think, last night. And by the time I woke up, a student had already got to it. So that was good, because that means we all get faster responses. Okay, I don't think there's any other administrative things to take care of. So I'm going to switch back to sharing the OneNote page. There, I think you guys can maybe see the OneNote again. Okay, so we left off yesterday at starting with one-dimensional motion, one-dimensional kinematics. So just as a reminder, kinematics is the study of trajectory. It's not necessarily the study of what causes motion or what stops motion. It just says, assuming something's already moving, where is it gonna go? Is it gonna, just do a little arc, go like, whoop, and then stop? Or is it gonna, hit a home run and hit the ball out of the park? Type of thing. So it studies motion. We talked a little bit about frames of reference yesterday. We were a little bit rushed finishing our last lecture, so that was my apologies. I went back and I looked at the problem, and I noticed a small inconsistency. It wasn't necessarily a mistake. I just wasn't careful enough reading the question. So if you look here, I'm going to be looking down, not at the camera. I'm going to be looking at the tablet while I'm writing, so I apologize for that one. If you look at this question here, hopefully I'm sharing this properly. I assumed, I wrote out my givens here on the left-hand side. I assumed that the boat's speed compared to the ground was positive, which fine. But I also assumed the water's speed compared to the ground was positive. You'll see here that, I inherently wrote a positive one. Oops. I inherently wrote a positive one there. So that, when I wrote my givens there, I assumed that the water was traveling in the same direction as the boat. And if you think about it, if the water is traveling at 8 meters per second and the boat's traveling 8 meters per second in the same direction, then if you look down at the water beside you, it won't look like it's moving at all. So that's why it was, we got an answer of 7. Now, when I reread the question, I noticed that there was a little bit of wording that I neglected to consider, and this is a good illustration of kind of the subtlety of wording in physics problems. It says a motorboat is traveling upstream, and the word upstream there implies that you are going against the current, which means that when I wrote my givens, I really should have been more careful. Oh, that's a terrible equal sign. Water compared to the ground. I really should have said this was -1 meters per second, because it's in the opposite direction as the velocity of the boat. And everything else is still the same that we've done here. This is the same equation, and I'm being a little bit sloppy with my notations. I should really be writing vector signs over those. However, when we substituted our value in, we had this thing to consider here, where we said we have the velocity of the ground compared to the water. We don't have that as a given. We have water compared to the ground, not ground compared to the water. So we had to flip the reference, so that added a negative. So I'm going to go back and just write a few more steps for you guys. So velocity of boat compared to the ground, vector. And then I'm going to say, velocity of boat compared to the ground, vector, minus velocity of water compared to the ground. And that negative sign popped up because I flipped the frame of reference there. And if I had to write a few more steps for you, just to make this a little bit more clear, now when I drop the vector notation, I am going to assign a direction. So maybe over here in the margin, I'll say, upstream equals positive. And if upstream equals positive, then I say, okay, well, the first vector, v boat compared to ground, that is upstream. So when I assign a value to it, I can say it's just going to remain positive, v boat compared to the ground. And notice this time I'm not writing a vector sign. I was a little bit sloppy yesterday. That is my apologies. And then minus, and then v water compared to ground. The minus sign is already there from before. So now we're just looking at the vector v water compared to ground. V water compared to ground. Oh, this is already disappearing. I don't know why. Okay. So v water compared to ground, it's traveling not upstream. It's obviously traveling with the stream because it is the definition of the stream. So that itself is going to be negative. So, you know, we add another negative there, two negatives, or I'll write it separately. Negative v water compared to ground. And now you notice that I'm not writing the vector signs because they're no longer vectors. Now they're just scalars. Now we just plug in the values as we see them in the written version of the question. We now no longer have to worry about plus, minus, plus, minus. We just take all the magnitudes and written in the question because we've dealt with all of the plus minuses when associating with the direction. I just need to enter some space here because we're running out of space. There we go. So simplifying this a little bit, I'm going to get v boat compared to ground, minus minus gets a plus, v water compared to ground, and this is, of course, 8 plus 1. These, again, are taken. I'm going to change my color temporarily. These, again, are taken straight from the wording in the question. And, of course, this equals 9 meters per second. And this is a word problem, and we did kind of have to get rid of the vector notation and introduce some of the plus minus convention. So it's always good to sort of finish off the question with saying, therefore, the boat's speed compared to water is 9 meters per second. And then that just packages it up for the reader in a nice, clear, concise way, because communication is important. Otherwise, you know, if you don't know what the number represents, why are we doing it, right? Okay, so that wraps up kind of what we started yesterday, and I fixed my rushing mistakes. So we're now going to move in to a discussion of an average quantity that we measure versus an instantaneous quantity that we measure. And I promise you all that we definitely have a notion of what this is. We may not have formalized it in a classroom setting for you up until now, but we definitely have experience with this. So hopefully I'll give you some concrete examples of things in your day-to-day lives that distinguish the difference between average and instantaneous. Now, I'm going to slide that slower. Now, hopefully, by the time I'm done explaining the differences here, the picture that I chose for this slide, hopefully that'll make a little bit more sense. But before I explain the picture, let's just do a little bit of formalizing here. So first, I'm just going to, now that it's new material, it's not review of old material, I'm going to change my ink to black. The red above was just indicating that it was different than yesterday's video. So the average versus instantaneous. Let's first start with defining the average value. And as students, I know, because I remember when I was a student, I was all over what my average was in the course. You know, what's the test average? You know, hey, professor, what's the test average? Or even calculating my own average. We all have this idea of what an average is. Let's consider something like tests. Let's consider 4 tests in a course. My handwriting is not very good on a tablet. My apologies. Hopefully I improve over the semester. So if we consider four tests in a course, let's say we want to know what our average test score is. So if we want to compute our average test score, we obviously just add up test number 1 plus test number 2 plus test number 3 plus test number 4, and we divide by 4, right? That's nothing new. Hopefully we don't need to be reminded of what a discretized average is. And of course we divide by 4 because this is the number of elements that go into the average. So when something is discretized or discrete, that means we can count them. They're individual objects or items. So I can say, yes, we have test 1, we have test 2, we have test 3, we have test 4. There's no such thing as test 1.5, right? They're discrete, they're different, they're distinguishable. What if we have a continuous variable? Well, a continuous variable might be something like, for instance, an object's velocity with respect to time, or position with respect to time, or acceleration with respect to time, just to name a few. But really, any function that is continuous with time would constitute as something measurable and is continuous. So if something's continuous with respect to time, how do you add them up like we did with the test? You can't say, f of 1, f of 2, f of 3, f of 4, because there are so many values in between f of 1 and f of 2 that we're missing. Okay, yeah, maybe you could add f of 1, f of 1 and a half, and then f of 2. Okay, still, there are infinitely many points between f of 1 and f of 1.5. And no matter how many points you sit there and include, you're never going to include them all. So you might recall from taking first year calculus and from the poll yesterday, I think it's pretty safe to say everyone is at least finishing their first year here at university. So hopefully everyone's had at least first year calculus. Some of you perhaps more recently than others. I will reassure everyone now though, don't worry, this is not a calculus-based physics course. I'm only providing you with the high-level background. Hopefully that improves with your understanding of the formulas, but I will never be testing you on calculus. So before I get any questions about, do I need to review first-year calculus? No, you don't. But if you happen to remember some themes from it, I will try to sort of connect the dots between your first-year calculus and this physics course here. So you might remember, and I will remind you if you don't, but you might remember from first-year calculus, if you have a continuous function and you want to know, and you want to add up all the y values as if we're adding up test 1 plus test 2 plus test 3 plus test 4, the way you add everything up, you add up values on a continuous function is we perform the integral. Right, so an integral is a way that we can add up all of the y values of a continuous function. And we do know the average is always the sum divided by the number of elements. Right, so that's what average is, the sum divided by number of elements. Well, for a continuous function, we know what the sum is, right? It's just the integral. So it's going to be the integral, let's say, from a to b of f of x dx. But the average also includes a division by the number of elements. So how do you count how many elements went into the integral? I mean, I've already told you that there are infinitely many points. There's like f of 0, f of 0.0001, 0.000001. Like there's infinitely many elements. Do we divide by infinity? No. We simply divide by b minus a, which would be the length of the domain that we integrated over. So this is actually the formula for the average value of a function, right there. And this equation is reflected in the course notes. I think it's definition 4.1 in the course notes that I've typed and posted for you. So let's use this equation, and let's do example 3. Oop, too big. There we go. Okay, I anticipate we're going to need a little bit more room here. So I'm just going to give us some space. Okay, so what is the average velocity of an airplane that flies 602 meters east in 2.5 seconds? Now, you might remember from grade 11 physics or grade 12 physics, or even just a basic understanding of speed, that you can just take distance and divide it by time, right? However, let's go through the motions. So I kind of want to show you where that equation came from. So we're asked here for, what color am I on? I'm still on green, aren't I? Let's go to black. So we're asked in this question, what is the average speed, V average? So following the formula, V average is going to be the integral of V of t dt from time 1 to time 2 over time 2 minus time 1. There we go. Now, this V of t, it's an arbitrary function of time. We don't know what it is. However, we know that the integral or the antiderivative of velocity will be displacement. And if that notion kind of confuses you, you can actually think of the reverse. If I have my position with the function of time, you know, let's say I'm here in my office at time equals 0, and I can get halfway down the hallway over there in 5 seconds, you can take the derivative of that to find speed. So, you know, one's a derivative, one's an integral, depending whether you go one way or the other. So we know that the integral or the antiderivative of speed is going to be displacement. So although I don't know what the actual formula is, I can just represent this by saying this is going to be the displacement as a function of time from time 1 to time 2, it's a definite integral, over time 2 minus time 1. And the way in which you handle definite integrals is you evaluate the upper bound, you subtract the lower bound. So this is going to be d of t2 minus displacement at time 1 over time 2 minus time 1. And just to tie in math a little bit, this is actually rise over run, so it's actually delta y over delta x. And instead of using math notation, delta y over delta x, because that's very much a math notation, we can acknowledge that this is here displacement at time 2 minus displacement at time 1. That's just simply the change in displacement. And t2 minus t1, again, is just the change of time. So this means the average velocity is exactly what we showed you in high school, is just delta d over delta t. Now, the reason why I present this calculus derivation is because every single year I always get a handful of students that try to use v equals d over t to calculate instantaneous velocity. And that's just simply not what that equation does. So hopefully showing you kind of where that equation comes from kind of reinforces the concept to you that this is an average, right? It's not instantaneous. Now, again, if calculus isn't your forte and it's been a while since you've taken calculus, or even if it was recent and you just, you know, didn't feel so confident in the calculus material, it's okay. I will not be testing you on calculus. However, I'm just hoping it gives you a bit of a background from what these equations are, or where they're coming from and where they're used. So anyway, now that we have this equation, to answer the example problem, it's fairly easy. We can just plug in 602 meters divided by, what was it? I think it was 2.5 seconds. And again, if you had a calculator handy, you could just easily calculate this. I believe it would be 241 meters per second east. And if you didn't have a calculator, you could invoke the lesson we did yesterday on estimating. So you might round 600 to, or sorry, you might round 602 to 600, and you might round 2.5 either down to 2 or up to 3. It's, I don't know, 6 of one, half a dozen of the other. So it's an estimation, right? So you could estimate it however you please. Okay, so I'm just going to pause for a second. We have a polling question coming up next. So, but before we do the polling question, I'm going to pause, and I'm just going to take a look at the chat here. I'm just, so the chat's open on my window. Thank you, Brandon, for handling the questions up until now. If you want to ask me a question, I'll read it directly, and that way we can clarify any questions before we move on. Why is E included in the answer? That's the direction, right? So the displacement in the question said the airplane was traveling at 602 meters east. So the average velocity is also a vector. So the velocity is 241 meters per second east. You could say, what's the average speed? The average speed would simply just be 241, but the average velocity would be a vector as well. So ideally, you should have a direction there. Any other questions before we move on? Oh, someone's saying, wouldn't it be 240 for sig figs? Screw sig figs, honestly. When we're doing questions like this on paper, you know, as long as you have a reasonable number, like don't be listing like, 4 or 5 decimal places. Obviously, that's just a little bit too precise. But whether you do 240 or 241, it doesn't really matter. Some people might care about that. I certainly don't. I will preface that, though, with saying if you're doing calculations on the lab reports and you do propagation of uncertainty and propagation of error, really the whole point of doing propagation of uncertainty and error is to keep track of the significant digits. So when you're doing calculations in a lab, for research, precision is definitely important. But when you're doing questions on paper, doesn't matter whether it's 240 or 241, but when you're in a lab setting and you're making an airplane because you're in the whatever, those details matter. But for this course, I'm not too concerned about sig figs. Okay, any other questions before we move on? The midterm will be hard, and oh yeah, that's just Brandon. Yeah, he's right. He's 100% right. The midterm will be, I don't want to say hard enough. I don't want to scare you into saying it's hard. I mean, it's a midterm in physics, so it'll be a midterm in physics. But Brandon's right. I mean, having you worry about setting up the question, drawing your free body diagrams, knowing how to solve the question, and showing enough steps and writing therefore statements. I mean, you'll have enough to worry about. I don't want to bog you down with significant digits. I just don't think that that's a good use of any of our time. Do we have a tutorial today? I'm going to assume you missed the beginning of the lecture. This week, we do not have tutorials if you look at the schedule. Yeah, thank you. Another student piped up. Thank you for that. Okay, it doesn't seem as though there's anything pressing. So I'm going to move on, and we're going to do a polling question. Now, yesterday, I know some of you were saying that when I hit the polling question, it covered the slide on the screen. Perhaps maybe we can, you can open up the PowerPoint, the Kinematics _PPT PDF on a phone or on a different device, and then that way you can have the thing in front of you. It just, hopefully it's easier that way. Maybe this isn't too, hopefully that's not too small. Maybe if I shrink the slide on the screen for you, when I open up the polling, maybe you can still see part of the question. So I'm gonna just start the poll now. So the question is, if the average velocity is non-zero over some time interval, does that mean that the instantaneous velocity is never zero during that same time interval? So I know we haven't talked explicitly about instantaneous yet, but this is sort of just to get your feet wet, right? Before we talk about the actual theme, I kind of want to get a sense of prior knowledge, how much prior knowledge you guys have. So average velocity, if the average velocity is zero over some time, does that mean the instantaneous velocity is also never zero for all the times in that interval? A is yes, B is no, C is it depends. So 113 of us have voted so far. I think there's about 143 of us in the lecture, so I don't know how long I should wait. 119, 120. Okay, so for the sake of time, I think that the responses are petering off. So for the sake of time, I'm going to end the poll and then share the results with you. Okay, so there you go. A whopping 79 or essentially 80% answered B, no. And in fact, that is the correct answer. It is no. And yes, I mean, the answers are on the slide, so I suppose you could just scroll to the next slide and see the answer. But that's obviously not the point of this. I mean, this poll is anonymous. There's no marks for it. You know, let's just participate honestly here. So let's see why this is the case. I'm going to stop sharing the results here so you all can get your screen back. So the average velocity is non-zero over some period of time. That just means the object moved. That's all it means. Now, does that mean the instantaneous velocity was always non-zero? Of course not. You know, for instance, you know, I clearly woke up in my house and got here on campus at some point today. So that's an average velocity. My distance d0 is at my house, and then d of time 2 is here. I think it's about a 15-kilometer drive, so I guess my delta d would be about 15 kilometers. And I arrived here at around 9 o'clock, and now it's around 11:30. So that's 2.5 hours. So my average velocity is low, but non-zero, and yet meanwhile my instantaneous velocity is 0. I'm sitting here stationary in a chair. So that's what that means there. For those of you who answered C, it depends. Perhaps what you were thinking is there are some cases when it is the case when the instantaneous speed is also never 0, and there will be some cases when it is 0. That perhaps is what you meant, but the question here is, does it mean that the instantaneous velocity is never 0? Meaning, is it always true to say this? So the answer is no, it's not always true to say this. So let's use a conceptual example. Oops, I don't know how to make this bigger. Hold on. Oop, too big, too big. There we go. Let's use a conceptual example to compare instantaneous and average speeds. So I have family that live in Ottawa, and I drive to Ottawa reasonably frequently. So let's say Mark was able to drive from Mississauga to Ottawa. Now I use Google Maps. It says it's 508 kilometers. And I was able to drive there in 6 hours. So if you do the math, that makes the average speed about 85 kilometers per hour. You're simply dividing 508 divided by 6. So that's about 85. Does this mean that Mark obeyed the speed limit the entire way? Well, if you recall what I said yesterday when I was talking about relative motion and driving on roads, I tend to go above the speed limit. I won't say by how much, but I tend to go above the speed limit. So if you know me at all, you know the answer is probably no. This does not mean that Mark obeyed the speed limit. But let's use physics to sort of kind of quantify this a little bit. So there's a few scenarios here, right? The average speed does not necessarily provide any information about the instantaneous speeds. So knowing that the average speed is 85 kilometers per hour doesn't actually tell us anything about my instantaneous speed at any point along the way. So let's consider some scenarios. We call those edge cases or boundary cases. So let's say Mark spends 3 hours driving to Kingston. And it's 3 hours of solid driving is a lot of work. So maybe I take a lunch break in Kingston. Maybe I'm really tired, so I take a 2-hour lunch break in Kingston. Okay, so 3 hours driving to Kingston, that's 3. And then 2-hour lunch break, that's 5 hours total during my trip. And I've only driven to Kingston. And we know from the question, I get all the way to Ottawa in 6 hours, which means I drive from Kingston to Ottawa in my last hour of travel. So that total is 6 hours. Well, in that case, I will have traveled from Kingston to Ottawa in 1 hour. And if you use Google Maps, the distance between Kingston and Ottawa and the average time of 1 hour, I would have had to be driving at 184 kilometers per hour to get from Kingston to Ottawa in 1 hour. So it's 184 kilometers from Kingston to Ottawa. So in that scenario, I would have been speeding from Kingston to Ottawa, quite a bit speeding. And but however, my average velocity is still 85 kilometers per hour. I started in Mississauga and I ended in Ottawa within 6 hours. So my average velocity is still 85. Now consider the other scenario. Mark leaves, or I leave Mississauga, and I drive with a constant speed, which is obviously impossible because, you know, there's stoplights or stop signs even getting from my house to the highway. But let's just pretend I have like a straight ramp from my house to the highway, which would be everyone's worst nightmare. Let's assume that I traveled at a constant speed all the way, in which case my instantaneous speed is always 85 kilometers per hour. And in which case, in that scenario 2, I would not be speeding at all. So giving an average speed doesn't really tell you a lot, anything really, of my instantaneous velocity. So although I didn't write anything here, I will say on the OneNote here, I'll say see example 4 in typed notes. So example 4 in the typed notes will kind of reiterate what I was just saying there. Okay, and then now we can actually talk about instantaneous. Oop, I just minimized something on my end. There we go. So now I'm going to talk about instantaneous velocity. So instantaneous velocity, hopefully you remember a little bit of grade 12 calculus and vectors because it was discussed in grade 12. It was also retaught in first year calculus. This is actually going to be the slope of the tangent line. So I'm going to write that in a different color. So when you have an instantaneous quantity measurement, this is actually going to be the slope of the tangent line. And the way in which this is achieved is by taking the derivative. Now, I think a lot of you would agree that derivatives are easier than integrals, and derivatives are also taught in high school, which everyone, at least most of you have taken calculus and vectors in high school, although it may have been a few years ago at this point, but that's okay. So the technical definition, I'm going to change back to black now. The technical definition of an instantaneous value is f of x is going to equal the limit as delta x goes to 0 of the change in the antiderivative capital F over delta x. Now, I could write this a little bit differently. I could write this as f of x2 minus f of x1 over x2 minus x1. And of course, I forgot my limit here. There we go. Perhaps the second way I drew this equation is a little bit more insightful. I'm going to draw a quick Cartesian graph here to remind everybody kind of what this means graphically. So if I have some sort of function like this, and I have 2 points, let's call this point x1, and let's call this point x2, then f of x2 minus f of x1 is just the difference in the y values. So that's going to be that, the difference in the y values. And then x2 minus x1 is the distance, obviously, the length. And then we would just simply connect these two. To get our, and this is called a secant line. The line that connects two different points on a graph is called the secant line. And the slope of the secant line measures the average rate of change. This is what we were talking about before. However, here we see when x1 and x2 become the same number, right? When delta x goes to 0, when x1 and x2 become the same number, this becomes the tangent line. So I'm going to just choose a different color now. If x2 becomes x1, then we now get Oh, I did not draw that tangent line very well. Tablet writing, what can I say? It's not very precise. So the blue is going to be the tangent line. So the slope of the tangent line is actually the instantaneous rate of change of a function. So really what I'm saying here is if you have a displacement function, d of t, and you want to know the instantaneous velocity, all you have to do is take the derivative of d of t and then plug in time equals, say, 10 seconds or 0 seconds, meaning like in the initial speed. So if you want the instantaneous speed at any given time, take the derivative of displacement and then plug in whatever value of time that you're looking for. So there's not a whole lot else to say about that one. Now we have to move on to acceleration. Oh, sorry, there is something I want to say about that. If we scroll up a little bit, where is it here? There we go. If we scroll up a little bit and we zoom into my slide here that I chose, hopefully the slide now makes a little bit more sense. This is what I chose to represent the topic of average versus instantaneous, right? It's a picture of a graph that you might see in calculus class. And there's different points listed on the graph, P1, P2, P3. Actually, there's no P3, P4, and P5. And at each of these points, there is a small tangent line that's drawn. And each of those tangent lines, the slopes of those tangent lines would represent the instantaneous rate of change of this function. So let's say this function represents displacement, and that means the slope of each tangent would represent speed. And if you were to actually integrate and add up the area under the curve and then divide by that time, then you get the average speed instead of the instantaneous speed. So I was just putting that picture there to hopefully remind students of the connection between, you know, what you've perhaps learned in the calculus class and what we're learning here. Okay, next up is a topic that's actually arguably the fundamental cornerstone of kinematics is acceleration. So here you can see that I've annotated this with not even a picture, just it all starts from here. So I told you before that kinematics is the study of trajectory. Assuming something is moving, where will it go? So clearly that's the end game of what we're looking for is d of t. We want to know d of t. We want to know the displacement of the object with respect to time. Where will it go? D of t. So if we just assume we start with knowing d of t, then we're done. We have our answer. So there's really nothing to study if we assume that we've started with displacement, because then we just have it, right? Well, then velocity then. If we assume we don't have displacement, because why would we assume we know the answer? Let's assume we don't have the answer, so let's assume we have velocity then. Well, if we had velocity, we could easily solve for displacement, and I just showed you how you integrate, right? They're inverses of each other. However, knowing what velocity as a function of time is a little bit easier than knowing displacement, but it's, again, not very common. However, acceleration, this is what I'm saying, it all starts from here. Acceleration is actually quite easy to measure in real life. We've got instruments, you know, easy ways to measure acceleration of various things. So this is what we kind of assume we're starting from. We assume that we're starting with knowing the acceleration of an object, and we're trying to predict with this amount of information, only the acceleration of the object, where it goes from there. So our analysis really all starts from knowing the acceleration, because if we just assumed we knew displacement, we'd have nothing to do. We would just be done, right? So before we get into the nitty-gritty of acceleration, I just want to do another polling question with you guys to see kind of what kind of pre-existing knowledge you have coming in, and everyone's coming from different backgrounds. So I just kind of want to get a sense of the prior knowledge here. So I'm going to start the poll again. Hopefully it was helpful that I kind of reduced the size of the slide last time. Maybe that was allowing you to continue to read it when the poll was up. So I'm going to do that again. And I'm going to start the poll now. Relaunch poll. There we go. So it should come up on your screen. So when you throw a ball straight up, which of the following is true about its velocity and its acceleration, specifically at the apex, or the highest point. So when you throw a ball and it goes up and it comes down, what is true about the acceleration and velocity at the top of its trajectory there, at the vertex of that parabola? And yes, I know you could all probably just scroll down and make it look like you got the right answer. That doesn't do anybody any good. You know, I don't know who's voting with what. It's a completely anonymous vote. So please try to just answer honestly. It's a good learning tool. Okay, so we have about 121 out of 142. I think we got about that last time as well. So I'm going to stop the polling then for the time's sake, and I'm going to share the results with you. So we have a whopping 62% of you saying C, and the other, I guess, secondary winner, it's a substantially lower percentage, is 23% with A. So let's look at this. It's saying at the apex, the speed is 0 if I throw it straight up, as well as the acceleration. So let's think about what that would mean. If the speed is 0, then that means the object would currently not be moving. And I think that makes sense. In fact, I know that makes sense, because the object on its way up would be traveling upwards, and then eventually the object would be traveling downwards. So at some point, there has to be, you know, a positive speed up and a negative speed down. At some point, there has to be 0, and that would happen at the top. So yes, V equaling 0 at the top absolutely makes sense. Now, how about A equaling 0 at the top? If the acceleration if the acceleration was equal to 0, then that would mean the rate of change of V, right? Because acceleration would be the derivative or the instantaneous rate of change of speed. If A is equal to 0, then the derivative of speed is 0. It will not change. The rate of change of speed would be 0. So we can all agree that the speed at the top is 0. And if the acceleration was also 0, then the speed would just remain 0 forever, because the rate of change of 0 is 0. It would just stay there. Now, answer C is a little bit different. Answer C says the speed at the apex, or at the top, is 0, which makes sense, but the acceleration is non-zero, meaning the rate of change of the value 0 is non-zero, meaning a moment later in time, the 0 value will change and it will start moving again. And last I checked, if I throw something straight up in the air, it doesn't just hover at the top. And that, oh, don't even get me wrong, that would be so cool. Every time we throw something up and as soon as it comes to the altitude there, it just kind of stops. That would be amazing. That would be such a cool life that we live in. Okay. Yeah, someone walked in. So clearly that A can't be right, because the acceleration at the top can't be 0, because then the speed would just kind of sit there and hang forever. So we know that that's not true. I'm going to stop sharing the results now. Okay, so that's the next slide here just confirms that C is the answer. Now, I ask you a bonus question. What is the value of A in this case? Some of you might know this from high school. I'll give you a bit of an answer there. It's little g 9.8 meters per second squared. That's just the local acceleration due to gravity. We will get there later in the course. So if that's not something you know from before, then that's okay. Okay, now that we've done that, I just want to, come on. Let's talk a little bit more about acceleration. I'm going to need a lot more space than this. Okay, well, we'll start with that for now. Okay, so let's talk a little bit about acceleration. We know that A is going to be equal to the derivative oh, I'm still on, there we go, sorry. A is going to equal the derivative of the velocity. So A equals dv by dt. And again, this is not a calculus course. I'm just showing you the background to give you some context to these equations. And we know velocity itself is actually the first derivative of position. So I could say A equals the derivative of speed, but it also equals the second derivative of position with respect to time. So this is kind of where everything starts. And this is actually called a differential equation. So if you want the technical terminology, it's called the differential equation. Now, what we can do is we can actually solve our differential equation and solve for x. So, you know, let's assume we have the acceleration because that's something that's easily measurable. So let's assume we have a. So assume we have a. And we're trying to solve for the displacement. So that means we first can solve for the speed as a function of time by integrating v of t dt, like that. Okay, sorry, that's not right. There we go. V of t equals the integral of a of t dt. Sorry, that makes more sense than what I wrote. Now, we have to make a little bit of an assumption here. In general, is acceleration always constant? No, it's not. When you're driving a car, hopefully when you're driving a car, acceleration isn't constant. Otherwise, you would just keep going faster and faster and faster and faster forever. That would become very dangerous. So in real life, acceleration is obviously not constant. However, let's simplify our analysis a little bit, and let's make an assumption here. I'm going to say assume constant acceleration. And there is actually a lot of times in real life, in the physics realm, I guess, that we would experience in real life where acceleration is constant, and we'll talk about those shortly. So let's just assume now that a is constant. Well, then our integral becomes the integral, instead of a of t, it's simply just a, because it's just a constant. So for all times t, a is just a. When a is, well, sorry, when t is 10 seconds, a is still a. When t is 0 seconds, a is still a. And what's the integral of a constant? For those of you who hopefully remember some basic calculus, the antiderivative of a constant is just a constant times the variable. And we, of course, get an integration constant. And the way in which you can remind yourself that you get that integration constant is if you were to take the derivative of this, you would get back a, and the c would disappear. But for any value of c, you'd still get the same derivative. So if you're going backwards, like integrating, you have that integration constant. And, oh, I need more space. There we go. So we have this integration constant, and we deal with this with something called initial conditions. And initial conditions mean, is there something that we know is true at the beginning when time is equal to 0? So when time is equal to 0, we have v of 0, when v of t equals 0. So this is going to be a times 0 plus c. So v at 0 is simply going to be equal to c, this integration constant c. So using our physics brain, we think to ourselves, at time equals 0, what does that represent? The initial speed, right? The object's going to have an initial speed when it starts at time equals 0. So we see here that when we plug in time equals 0, the equation simplifies to c, this integration constant. So we know in real life, this actually has a physical meaning. The physical meaning is initial speed, vi. I think in the type notes, I perhaps used v naught. So I might use v naught here as well, because I think in the type notes I used v naught. So this becomes at plus v naught. There we go. So starting with constant acceleration, I know that my speed will take on linear a linear form. So my speed will increase linearly if I have a constant acceleration. Now, our end game with kinematics, again, I can't stress this enough, our end game with kinematics is getting trajectory or displacement with time. So we don't quite have that yet. We still only have speed. So we note that, we note that the derivative of position is equal to speed. And we just solve for speed, at plus v naught. So we actually have the derivative of position, which means if we want to solve for position, all we're getting, or all we need to do is integrate v of t dt. And the last time I did this, last time I integrated, that is, just above, I had to assume my acceleration was constant because we didn't have a formula for acceleration. This time we have a formula. So assuming a constant acceleration, we get a linear speed, and now when we integrate, we're simply just integrating a line. So we're getting, we're getting the integral of a times t plus v naught dt. And again, we are running out of space. Okay, so integrating a line is relatively easy. We get a, and the antiderivative of t is t squared over 2. The antiderivative of v naught, which is a constant, is going to be v naught times t. And then we get that integration constant again. So there you go. Now, we're not totally done yet because we have that integration constant. So we do our initial conditions again. And we know at time equals 0, whatever x of 0 is, we know is going to represent the initial position of this object. So when we plug in time equals 0, we're going to get a over 2 times 0 plus v naught times 0 plus c equals x naught, the initial position. So this actually means that x naught is just equal to c. So I could say, therefore, my position with a function of time is going to be a t squared over 2 plus v naught t plus my initial position. And there you have it. We have now achieved our goal. Our goal, we set out on this journey to say kinematics is the study of trajectory. Assuming something's already moving, right? We've already assumed it has an acceleration. We don't know where that acceleration came from. We'll worry about that later. But assuming something's already moving, where will it go? This is where it will go, okay? Now, perhaps in a physics textbook or in high school, they packaged this equation slightly differently. So I could rewrite it just a little bit differently if it helps you. I could say something like x of t minus x of 0 meaning my initial time, so x naught, is going to equal v1. Instead of writing v naught, I'm going to write v1 just because I'm trying to show you how it might relate to what you've seen in high school, plus 1/2 a t squared. And of course, x of t, which means the position at some future time t, can be thought of as like d2, the displacement 2, and x naught could be like displacement 1 equals ... And then d2 minus d1 is simply delta d equals v1t plus 1/2 a t squared. And this is the equation that is shown in most textbooks. So they're really the same equation. They're no different than one another. The two boxed equations here are identical in every way. It's just a different way to represent that. So just to summarize here, I just want to remind you that the displacement of an object ends up being quadratic, but only for an object that is subject to constant acceleration, right? Our whole analysis here hinged on the fact that we assumed a constant acceleration. If we didn't start with a constant, well, the integral of a constant is a line. The integral of a line is a quadratic. If we didn't start with if we didn't start with a constant, what if we started with, a hyperbolic function, 1 over x? Well, the antiderivative of 1 over x is ln. So that would mean my velocity is logarithmic. And then integrating ln is no trivial matter, but its result would definitely not be quadratic. So when you study kinematics as a scientist or as a physicist, you don't necessarily always use the quadratic answer for displacement. You always have to start with the acceleration you're given and then integrate twice to go from there. So here we have a few equations that we've seen along the way. This is just to summarize. This is also in the typed lecture notes, by the way. So the first one here is the average velocity. It's delta d over delta d over delta t. When I integrated the acceleration once, I was able to get v equals at plus v naught. So another way of writing this would be, let me just use red here. Some books say v2 equals v1 plus at. That's, different symbologies, but that's fine. This is the one we just derived above. So you saw that derivation just above. This one here is not used very frequently at all. In fact, in all of my years of doing physics, I've actually never used this equation at all. It's technically valid, but I've never used it. So you don't necessarily need to worry yourselves about it. And the only one left that we haven't really talked about would be this one here. And this one's derived. They use the other equations that we've previously derived. They use v equals at plus v naught. They use the displacement equation that we just derived, and they plug the two of them into each other, and then they eliminate time is what they do. So this one here, I'm just going to say 1, 2, and I'm going to say use 1 and 2 to eliminate the time variable. So there's nothing fancy about that equation. There's no, intuitive physical derivation there. It's just plug and chug. It's just math. So these are the 5 kinematics equations, and every time you're doing a kinematics equation, either on a test or in your assignment or when you're doing homework, you should go and just kind of have these equations kind of off to the side, because really every kinematics problem is solved with a combination of these 4 or 5 equations. Assuming, of course, a kinematics object, it has a constant acceleration. If it's not a constant acceleration, then you have to reintegrate using the actual function for a. But everything in this class will have a constant acceleration, because it's not a calculus-based physics course, so that's good for you. So yeah, just use whatever equation suits your givens and your unknowns. Let's say there's a question I give you that has t and a and initial speed, and we want d. Okay, well then use the displacement equation. What if we give you v1 and v2 and a, and we ask for d? Well, we didn't give you time, so look for the kinematics equation that doesn't have t in it, right? So just use whatever equation that is easy for you there. Okay, so before we do some examples, I'm just going to open the chat here. Hopefully Brandon has been getting to that. Do we have a 10-minute break after an hour of lecture? Not usually. I know when we're in person we usually do, but evidently we're already pushed for time. It's already quarter after, and we're a little bit behind schedule, but no one's keeping you tied to your desk. If you need to get up and grab a glass of water or something, or grab a snack, you can always just kind of hear my voice in the background as well. Okay. Someone asked, the same guy asked if we have a tutorial again today. I thought we already answered that. No, we do not. Are there any questions about the acceleration, velocity, displacement. Do we need to know how to derive the 5 equations? No. To derive the 5 equations, you would need calculus. And I've already said that this is not a calculus-based course, so I would never ask you to mathematically derive these from first principles. I cannot see 5.4. Oh, Brandon, thank you. We will not have to use equation 5.5. I don't think so. I mean, it's there. It's mathematically true. It's just in all of my years as a physicist, I've never had to use equation 5.5. Can you explain why velocity is 0 and acceleration is not 0 for the second poll question? Yeah, I can quickly reiterate that. I thought I took a lot of time explaining that, but we can all agree that the velocity is 0 at the top of when you throw the ball up. That is, we can all agree on that one. So I think the question there is specifically, why is the acceleration non-zero? Well, the best way to explain that is to assume the opposite and see why the opposite is not right. If we assume the speed is 0 at the top, so let's say I throw something up. At the top here, the speed is 0 momentarily, but let's assume the acceleration is also 0 at the top. If the acceleration is 0 at the top, then the rate of change of speed will be 0. So if the speed is 0, and the rate of change of speed is 0, then that means it's going to remain at 0, a velocity of 0 forever. And that would mean the object just hovers there forever because the speed is 0. But that's obviously not true. If you throw something up, it comes back down. So the speed is momentarily 0, just for a brief moment in time, because the acceleration is non-zero, meaning the instantaneous rate of change of speed is non-zero. So it's 0 for a small moment in time, and then a moment later, it becomes non-zero. The speed is negative, so the object comes down. That's also the condition of gravity. You know, gravity has a constant pull on all of the objects. So just because the object is at the top of its arc doesn't mean gravity doesn't work all of a sudden. So we'll never be tested on what we just did. Well, I will never ask you to use calculus to derive the equations, but the whole point of the lecture is to, you know, explain to students where all of the physics is coming from, how to think of the physics and how to use the physics. So no, I will never ask you to use calculus to derive anything, but, you know, it is good to understand where things come from for sure. So if you can get your head wrapped around the calculus, I would strongly recommend reviewing the background knowledge, because it'll help you apply these concepts. Okay, are there any other questions before we move on? Brandon, I'm not really sure what you're talking about. Whoever had a question, I couldn't see. Whoever had a question, no, I'm not sure. I'm not sure what's happening there. Why does equation 5.4 have 2 values after each v? Oh, because it's squared. V2 squared equals V1 squared plus 2AD. So V sub 2 is like the velocity at some future time 2 squared equals V sub 1, the initial speed, squared. So maybe that's what you mean by 2 values. Can you please give us some examples? We're about to do some examples. If you can see my screen, actually, I'm poised to do some examples next. But before we delve into the examples, I wanted to address any questions you guys may have had. Okay, so I think that handles all the questions. Let's move on and do some examples. I don't know why this isn't scrolling. Why is this? Ooh, geez, what's happening? Technology is not always, there we go. Okay, I think we're good now. So let's move on and do some examples. So let's start easy. During a hard sneeze, your eyes might shut for, I don't know, let's say half a second. And I don't know about you, but when I'm driving, there have been times when I have sneezed. And every time I'm about to sneeze when I'm driving, I think to myself, oh crap, my eyes are going to be closed for some amount of time. You know, let's hope nothing bad happens to the car or anyone else around me while I'm sneezing. So let's assume we're kind of at highway speeds, maybe 90 kilometers per hour. Let's see how far the car moves during this sneeze. So if I'm traveling at a constant velocity, let's see here, constant velocity of 90 kilometers per hour, and the time is half a second, we want to know how far it goes. So constant velocity means there's no acceleration, and no acceleration means we can simply use v equals d over t. I know technically this is the average velocity. However, this is why I specified, and I really want to emphasize this, when there's no acceleration, the average speed is the instantaneous speed because there's no acceleration. Every moment in time, you're traveling at exactly the same speed when there's no acceleration. So that's the case here. Maybe I've got cruise control on in my car or something, so the car is going at the exact same speed. So we're going to have 90 kilometers per hour divided by half a second. Oh, sorry, that's not right. We're going to have some amount of distance over half a second equals 90 kilometers per hour. Now, we're trying to solve for d, so then that means d is going to equal 90 kilometers per hour times half a second. And you'll realize when you multiply these numbers, the units don't cancel, right? We've got seconds on the numerator, and we have hours on the denominator. You can't cancel hours and seconds. So this is why we started the course off with converting units. So if we convert units, we've already done an example where we've got to convert kilometers per hour to meters per second. So hopefully you recall the conversion is 3.6. Specifically, you divide by 3.6. So this is going to be 90 over 3.6, and now this is going to be meters per second times half a second. So now the seconds will cancel, and half of 90 is 45, so 45 over 3.6, and this is going to equal about 13 meters. So when you sneeze on a highway, and during your eyes when they're closed, your car travels forward 13 meters. Now that may not seem like a lot to you, but you picture, in fact, I think I have a meter stick somewhere around here, right? Here's a meter stick. Picture 13 meters. In fact, a door, I think you can kind of see a door over here in the background. A door is about 2 meters tall. So 6.5 doors stacked, either length, like high. Picture 6.5 doors. When your eyes are closed, 6.5, your car travels 6.5 doors. That could potentially be a little bit dangerous, I would think. So, you know, when you're sneezing, it's kind of important to make sure you kind of open your eyes really quickly again, because you don't want to like veer off and hit anybody. Let's take this a step further. A lot of you live in and around the GTA, and even if not, hopefully you've been on some sort of train before or subway before. That's really the root of what I'm getting at here. Let's look at some of the physics that civil engineers need to consider when they're designing subway times. And I know in Toronto, everyone's always like, my train is 2 minutes late, blah, 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 blah. Well, you know what? There's a lot of different factors that go into scheduling times for subways. So let's spend a little bit of time here and look at some of the physics involved in planning the subway schedule. So here, let's say if the, well, actually, let me, I could handwrite the rest of the question, but I think that would be probably not to anyone's benefit. So let me copy and paste for you the rest of the question. Oops. Okay, so it should come up. There we go. So there's the rest of the question. A, if the maximum acceleration that is tolerable meaning safe, for the passengers is known to be 1.34 meters per second squared, and the subway stations have a known distance of 806 meters apart, what is the maximum speed that a subway train can attain? What's the maximum speed that the subway train can attain? So this is really the first kinematics question I'm doing with you. So let's just start writing out our givens. A good plan of attack and problem solving strategy is to just kind of list what we have and list what we need, and then look above in our resources to see kind of what equations we can use. So let's see here. We know that the acceleration of the train is allowed to be 1.34 meters per second squared as a maximum. If it was any larger than that, it would become unsafe. Maybe people standing and holding on to the rails, they might get jerked around or something if it's, any stronger than that. So that's the threshold. We also know that the distance between stations is 806 meters apart. And there's some sort of buried knowledge that we kind of have to flesh out. So we can say something like the initial speed of the subway train is presumably 0. I mean, it stopped at one subway station, and it obviously will start at 0. We also know that the initial position will, again, probably be 0, because why wouldn't it be? And there's a subtle layer to this. We're asked for the maximum speed, Vmax, maximum speed. Well, we can't just accelerate the entire 806 meters, because then it would reach the second station and just be going an amazingly fast speed, and you can't just slam on the brakes and stop the entire subway train in a fraction of a second, right? Even if you had brakes strong enough to do that, that would make the acceleration far larger than 1.34 meters per second squared, right? So here, because of this, because the maximum acceleration is only allowed to be 1.34, this means logically, and this is kind of the physics logic trick to this problem, this means we can only accelerate for half the distance. We can only accelerate for half the distance. Because if we were to accelerate more than half the distance, then we would have less than half the distance to decelerate, which would make our acceleration larger than 1.34. So, that would be a problem. So, in fact, this means that our D is not 806, it's actually 403. All right, so now that I've listed all my givens, I have A, so I'm just gonna maybe write this over here in green. I have A, I have D, I have V1, and I'm asked for V2. So I have this, I have this, I have this, and I'm asked for this. So now that I set everything up in a life logical way, I can see what I have and what I need, and then I can go back and I can look at the bank of equations that we need here, that we have access to, and I look at which equation has all of the right givens and unknowns. So time isn't a thing here. So any equation that has time in it, we don't need. So can't use this, can't use this, can't use this, right? Because there's no time. We don't have time in our problem. So then that means the only thing we have left to use is this one. We have V2, we have V1, and we have A, and, well, we don't have V2. We're asked for V2, we have V1, we have A, and we have D. So that means we are simply using, let me just change my font. That means we are simply using V2 squared equals V1 squared plus 2AD. And V2 is what we're looking for. So this is going to be the square root of V1 squared plus 2AD. And V1 we know is 0 in this case. So this is going to be the square root of 2AD. So there's my final equation. There's my final equation. It is always good to write your final derived equation before plugging in numbers. Not only is that just good practice for your problem solving skills and your math skills, it also is great, optimizes your communication, your scientific communication with the rest of the world. And if you need an even better reason, it helps your TAs give you part marks. Because if we can look at your equation and your equation's correct, and then let's say your calculator and you decide to have a love-hate relationship, we know that the mistake is with the calculator and we can give you like 9.5 out of 10. But if you plug in numbers here, plug in numbers here, plug in numbers here, plug in numbers here, and then kind of put them all together, it's really hard for us to figure out, you know, if there is a mistake, where the mistake is, because you kind of have numbers floating everywhere. So it's always good to have a final derived equation. And so that's what I have here. Plugging in all my numbers, 2 times my acceleration is 1.34, and my displacement is 403. And going through all of this, you're going to get 32.9 meters per second. If you had a calculator anyway, you'd get 32.9. Absolutely, if you wanted to, you know, estimate, like let's say the question specifically on the test said estimate how fast, you know, then you can start modifying some of the numbers like that. Okay, so that's part A. Okay, B. B said, if the travel time, oh, sorry, what is the total travel time between the two stations? So B said, what is the total time between the two stations? So now, starting this question, starting B that is, we have A, we still have A, we have distance, we have, what else do we have? We have the maximum speed, and we don't really have a lot else. Not really. Well, sorry, we also have the initial speed, V naught. So, and we're asked for time. So we need to look at our equations to see which equation has A, D, and V, and T. A, D, V, and T. So if we scroll up to our equations here, these are the 5 equations. Now looking at this, the one that has A, D, V, and T is this one, right? We have V naught, it's 0. We have A, it's 1.34. We have delta D, and we're looking for time. So let's use that one. Nope, too far. There it is. So the equation we're using here is going to be delta D equals V1T plus 1/2 A T squared. And we know V1 is 0, luckily for us. So this means delta D equals 1/2 A T squared. So solving for T, you're going to get T is going to be the square root of 2AD. Now, that right? No, it's not. That's not right. 2D over A. There we go. There we go. Okay, so there's my equation. And now I'm going to plug in some numbers. Now, here you got to be a little bit careful. What is the d that we use? It's not going to be the full distance because the acceleration over the full distance isn't constant. For the first half, the acceleration is positive 1.34, and then for the second half of the trip, it's negative 1.34, right? The train has to then slow down and come to rest to arrive at the next station. So the d here is going to be 403. It's going to be half of the total displacement. So this is going to be the square root of 2 times 403 over 1.34. And I believe this works out to be 24.5 seconds, something like that. Now, this is only the time for half of the total travel time, right? The first half from 0 to the midway point. So to answer the full question, I would say the total time, therefore, the total travel is twice 24 and a half, which is around 49 seconds. So roughly 49 seconds in between stops. So next time you're on the subway in Toronto or whatever city you're from, maybe just measure, if you're curious, measure, you know, when they say the doors close and as soon as the train starts moving, start a timer, and then right when the train stops, stop the timer and see kind of how close it is. Now, of course, there's different distances between train stations. So I was approximating a total distance of 806 meters, but, you know, depending on where you are and what city you are and, you know, the exact stops, it might be different, but it's under a minute, I guess. I would be surprised if it's much longer than a minute. And then, oops, not A. The last part of the question is part C. Part C says, I have to scroll up here. What did part C say? Part C says, if a subway train stops for 20 seconds at each station, what is the maximum average speed of the train from one stop to the next? So here we say there is a layover or a wait time of 20 seconds. Obviously, you need to wait for people to get on and off of the train, right? And when you're making a schedule for the train to post for the riders, you have to factor this time into account. So a wait time of 20 seconds, and we are asked for the average speed, question mark. We're asked for the average speed from stop to stop, because this is the number you need to report when you are you know, making a schedule. So the average speed, we know V average is going to be delta D over delta T. And the change in displacement between stop to stop is going to be 403 plus 403, right? It's going to be the full 806 meters, right? That's stop to stop, 806 meters. And the total length of time between, you know, leaving one station and leaving the next station. So the total length of time is going to be 49 seconds plus 20 seconds, the layover time. That's the total length of time. That's equivalent to me driving to Kingston and then taking a bit of a lunch break before resuming to Ottawa. You factor in that time into that. So when you do this math, you're going to end up getting, I believe, around 11.7 meters per second. Okay. So hopefully that was our first real worked example with one-dimensional kinematics. And we used 3 of the main formulas there. We used the V2 squared equals V1 squared plus 2AD. We used the displacement equation delta D equals V1T plus 1/2 AT squared. And then we used the very basic V average equals delta D over delta T. So that example sort of encompassed kind of everything we've talked about up until now. Okay, there is a more elaborate question, but we are kind of running out of time for today. So we will put a pause on this and maybe we'll do it tomorrow. But for now, I kind of want to move on to dynamics. just to kind of get us, not dynamic, sorry, two-dimensional kinematics. So we've been talking about one-dimensional up until now. I kind of want to get a move on into two-dimensional kinematics. So I'm going to stop the recording now because we're going to officially change topics into 2D motion. So this, I guess, concludes all of the information for the one-dimensional kinematics.